Hello, Stat 200, and welcome to Lesson 8. This week and next week, we will be applying the central limit theorem and using the z and t distributions to construct confidence intervals and to conduct hypothesis tests. When sample sizes are sufficiently large, these are the preferred procedures. This week, we'll cover the procedures used with one sample, and next week, we'll cover the procedures used with two independent samples. Let's start with a quick review. These are the general formulas for a confidence interval and a test statistic. This is the same general form of a confidence interval that you've been working with since Lesson 4. And this is the general form of a test statistic that you saw last week. All of the procedures that we'll review this week will follow these formats. These are the key topics that you'll learn about this week. These should look familiar because you've been working with these since Lesson 4. For each of these topics, we'll cover confidence intervals and hypothesis testing. In this video, I'm just going to give you a quick overview with the assumptions for using the common distributions that you learned about last week. Let's start by looking at some strategies. First, always start by assessing the research question. Identifying the variables correctly is key. There are quite a few questions on the quiz this week about selecting the correct procedure. You need to be able to assess the situation and identify the correct test before you can do anything else. Pay attention to the similarities. You will see many formulas between this week and next week. Always look for the similarities. The structures of the formulas for confidence intervals and test statistics are very similar this week and next. And when possible, use Minitab Express. Minitab Express can be used to do all of the calculations this week. For the lab assignment, and even on the quizzes and Widely Plus assignments, you can use Minitab Express. Now, we'll move on to cover this week's three key topics. We'll start with one sample proportion. If n times p and n times 1 minus p are both at least 10, the sampling distribution can be approximated using a normal distribution with the standard error of the square root of p times 1 minus p divided by n. Note that the way that we check this assumption is different depending on if we're constructing a confidence interval or conducting a hypothesis test. For a confidence interval, we do not have a value for p, the population proportion, so we use p hat. N times p hat is the number of successes in the sample. N times 1 minus p hat is the number of failures in the sample. So for our confidence interval, we need to have at least 10 successes and at least 10 failures in our sample in order to use the normal approximation method. If this assumption is met, then we can use this formula to construct the confidence interval. If we're conducting a hypothesis test, then we do have a hypothesized value for the population proportion, and that value is used when constructing the sampling distribution. When conducting a hypothesis test, we take the value of p sub o, which is the proportion in the null hypothesis, and we compute n times p sub o and n times 1 minus p sub o. These values must both be at least 10 in order to use this formula and the normal approximation method. Note that these formulas are both similar to the general forms that we saw earlier. If n times p or n times 1 minus p is less than 10, and recall here that p is estimated using the sample proportion when constructing a confidence interval or the null proportion when conducting a hypothesis test, then the sampling distribution can be approximated using a binomial distribution. Minitab Express refers to this as the exact method. We won't be using the exact method by hand in this course. Last week, we saw the binomial distribution. The exact method uses a binomial distribution as opposed to a normal distribution. For one sample mean, if the sample size is large, at least 30, or if we know that the population is normally distributed, then the sampling distribution will be approximately normal with the standard deviation of sigma divided by the square root of n, where sigma is the standard deviation in the population. Most of the time, we don't know the population standard deviation, so we estimate it using a sample standard deviation. The formula that you may see in these cases is S divided by the square root of n, where S is the standard deviation in the sample. Because we will need to estimate the population standard deviation using the sample standard deviation, we use a t-distribution to approximate the sampling distribution. A t-distribution is similar to a z-distribution in that it is bell-shaped. However, the height of the t-distribution changes depending on the degrees of freedom. For a one-sample mean test, the degrees of freedom that are used to determine the height of the t-distribution are equal to n-1. These are the formulas that we will use to construct confidence intervals and compute test statistics for one sample mean. Again, these follow the same general formats that we have been using for a few weeks now. If the sample size is small, less than 30, and we don't know if the population is normal, you should use bootstrapping or randomization techniques. In previous weeks, you have used these procedures in StatKey and in Minitab Express. In special cases, such as with standardized tests, the population will be normally distributed and the population standard deviation will be known. In those cases, the sampling distribution can be approximated using a z-distribution. When the population standard deviation is known, then you don't need to estimate it, and the z-distribution may be used instead of the t-distribution. This is known as a one-sample mean z-test. There's an optional section in your online notes this week that covers the one-sample mean z-test. This test is used often in the fields of education and psychology, where we have standardized tests with a known population mean and a known population standard deviation. In other fields, you may be much less likely to see this type of test. In Lesson 1, we looked at the difference between independent and matched pairs designs. Paired samples, also known as dependent samples, can involve taking two measurements on the same participant, or it can involve matched data, for example, mother-son pairs or husband-wife pairs. You've seen some of these examples in StatKey. StatKey treats these as a single sample means test because the formulas and the procedures are the same, with the added first step of computing the differences. Like the single sample mean test, if the sample size is at least 30, the sampling distribution can be approximated using a t-distribution. These are the formulas that we're going to use for paired means tests. Note that these are the same as the single sample mean formulas. Now we just have a subscript d for the mean and standard deviation. The subscript d stands for difference. The degrees of freedom will still be n-1, where n is the number of pairs. These are all of the formulas that you will see this week. Remember that Minitab Express will construct all of these confidence intervals and compute all of these test statistics for you. Minitab Express, however, will not check assumptions for you. You will need to check the assumptions yourself to determine if it is appropriate to approximate the sampling distribution using a z or t distribution. If assumptions are met, then these are the preferred methods. If assumptions are not met, then you would need to use the exact method if you're working with a proportion, or go back to bootstrapping and randomization techniques if you're working with a mean or paired means. This concludes the Lesson 8 overview video. As always, if you have any questions this week, please post them to the Lesson 8 discussion board on Canvas.